We're going to calculate the molar mass of a sample of gas under certain conditions. Now, if you think about what we've done so far, the combined gas law involves changing pressure, volume, and temperature. That doesn't help. Well, if you'd use the ideal gas law and the value of R, well, that doesn't seem to help. Molar mass has units of grams per mole. Well, I'll do what I did with the density problem, and I'll derive a mathematical formula for molar mass in a similar way. So you have to start with the ideal gas law. And then I'm going to divide the right side by the number of moles. And I'm not telling you why yet. We'll just kind of go with the flow here. And using the mathematical property of equality, that means I have to divide the other side of the equation by n also. And what this does is this allows me to cancel n on the right-hand side. So now I have the equation on the right. PV over n equals RT. And now I'm going to multiply by mass. Unless you've done this before, the reason for this isn't yet obvious. But if I do the left side by mass, I have to multiply the right side by mass. We'll see in a moment why. Okay, now I need to modify that one, so we're over in the bottom right. I'm going to divide the left side by PV, which means I divide the right side by PV. The reason for doing that is so I can cancel the pressure volume. Now, why go through all this? Well, look at what I have left on the left side of the equation. I have mass over moles. What are the units for molar mass? Grams over moles. That's why I inserted mass early on, and that's what I now have on the left-hand side. I have molar mass, so I'll write that as the italicized capital M. And that's equal to what was on the right-hand side. Now I have a mathematical formula that will allow me to use ideal gas information to calculate the molar mass of a gas. But similar problems, as I stated for the density problem, you either have to memorize this mathematical formula or you have to be able to figure out how to derive it. So I'm going to show you a different way, just like before, using unit analysis like we've been doing. Let's extract the information. The temperature, that has to be in Kelvin. The pressure, we are given the mass, so I'll go ahead and pull that out. And we have the volume. Well, since it's not a combined gas law problem, we need the value of R. And since the pressure units were given in torr, I'll go ahead and use the value of R that has torr in it. Starting like we've done on many of these problems, I'll write down the value of R, clearly separating my numerator and denominator. But maybe I have to divide by R, so maybe I need to take the reciprocal. Let's go back up and look at the information. We're asked to calculate the molar mass, which is units of grams over moles. And if you look down at R, Writing it this way puts moles in the denominator. Well, that's what I want because I want grams over moles. Now, let's do some unit analysis. Multiply by the Kelvin temperature. Divide by the volume. Divide by the pressure. And where are we? Well, we have units of moles left in the denominator. Oh. We need grams over moles, so bring in the given mass. Now, an alternate way to have done it up to this point is to actually have started with the ideal gas constant with the reciprocal, calculate moles, and then divide moles into mass. But that's what we really have here. And multiply and divide everything. And we get 70.7 grams per mole. 3 significant figures because of the 2.50 liters. Common sense check, make sure it's greater than 2. Greater than or equal to 2, because that would correspond approximately to that for diatomic hydrogen gas. Anything less than that, you've probably done a mistake. Now, I got the information from sulfur dioxide gas, and what I did is I took the density at the given temperature and pressure and scaled it up for this problem. But this is experimental information. Let's compare it to the actual density of sulfur dioxide gas, because I didn't tell you what the chemical formula was. Well, if I told you what the chemical formula was, we wouldn't need to go through all this. And sulfur dioxide's molar mass is 64.06 grams per mole. So this value we calculated, the 70.7, using the ideal gas approximation, actually gives us a value that's over 10% too high.